Robert Strain. He's going to talk about the 2D Peskin immersed boundary problem. Please go ahead.
Hi, so thank you very much for the invitation, and thanks a lot to the organizers for putting this conference together. It's been very interesting and informative to me, and I've enjoyed all the talks so far. It's been fun to wake up early in the US time to attend the conference also. So this is a kind of new area for me in terms of PDEs that I studied, and it's probably, at least for some people, something they may not have heard so much about. So if you don't mind, I'm going to explain a bit more in the beginning than I would say if I was talking about the Boltzmann equation. But so this is, I'm going to talk about the two-dimensional Peskin problem, which is also usually called the immersed boundary method or the immersed boundary problem. It was initiated by Charles Peskin, who's still alive and working at Courant. This is joint work with two different groups. One is Eduardo Garcia Juarez, who used to be a postdoc at UPenn, and Yoshiro Mori, who moved to UPenn from Minnesota a couple of years ago. And the other work that I'll talk about is a joint work with Stephen Cameron, who's currently a postdoc on the job market at the Courant Institute. Okay, so I started working on this when Yoshiro Mori moved to UPenn, and he was interested in discussing with me because this problem has a lot of similarities to other free boundary problems that I've worked on. And so let me just, without saying a lot about any of these topics, let me just put this situation of studying free boundary problems in PDE in the context of other problems that may be more well known to some people in the audience. So you have the Kelvin-Helmholtz problem, the water waves problem, and the problem of a Healy-Strauss cell, or sometimes this is related to the Muscat problem. And these are all sort of widely studied situations in the analysis of PDE that people know about if they that there are a lot of papers on. And then this situation in terms of the immersed boundary method is also a free boundary problem that has received a lot of mathematical and other attention, but almost none until recently from the sort of analysis of PDE community. And so the primary modeling modification for this is studying blood flow through heart valves, and in particular studying the evolution of red blood cells. And the main interests in and questions that we ask from the analysis of PDE point of view for all of these free boundary problems is so you start with some sort of boundary that right here in 2D, and you have an initial boundary that I call the boundary of D0, and as time evolves, how does the boundary, what happens to it over time, how does it evolve? And so questions that we want to understand and know the answers to are local existence, local and time existence and uniqueness of solutions, which we call well-posedness, then regularity of the interface, which is smoothing effects. Does the regularity of the interface break down, or does it remain smooth for all time? And then often you can prove global and time existence and uniqueness. Often, if the equation is very nonlinear with a small data condition, or sometimes even without a small data condition, you can prove global and time existence and uniqueness. And then we're also interested in the large time behavior. Does the equation converge to steady states, or does it Is it unstable in some sense? And we're also interested in answering all of these questions above for non-small initial data and understanding how the nonlinear effects come into play when the initial data might not be small. And an important thing to look at is a critical regularity. And so all of these equations will have an invariant scaling. That scaling will predict that certain function spaces, certain Sobolev spaces, or other types of function spaces are scale invariant with respect to the scaling of the equation. And then the question is, can you prove solve any of these questions, global existence or local existence at critical regularity? And so we're also interested in the effects of viscosity, and in particular when you have different viscosities inside and outside of the fluid, and how that plays a role in the solving of problems, and that induces a lot of non-local effects. Okay, so those are the main questions. Let me give you a few examples that may be more familiar than, say, the Peskin problem. And the first example that I want to talk about is Darcy's law. And so this is, Darcy's law is actually commonly thought of as the third equation, but this is the incompressible porous medium equation, where U, P, rho, and mu are U is the velocity, P is the pressure, rho is the density, and mu is the viscosity of the fluid. And then kappa and G are the other quantities above, and kappa is the permeability of the medium, and G is the gravitational constant. So G is the gravitational constant. It's being pushed down in the dimensional direction, and mu and kappa are the other constants. And then we're solving for rho, which is the density, and U, which is the velocity of the fluid. And this is the transport equation for rho, and then U is incompressible, and U satisfies Darcy's law. And typically this is the situation when you have a fluid flowing through a porous medium. So here these gray blocks are like the spaces that the fluid doesn't flow through, and then it flows through the rest. So this is one example. And another example of the porous medium equation is in R2, and it looks sort of from a PDE point of view almost exactly the same as the previous equation, except this is called a Healy-Shaw cell. And the parameters could be, they're still parameters, but they're not as general as on the previous slide. And the idea of a Healy-Shaw cell is, this is the picture, is you have a fluid between two large plates flowing, so it's flowing through in a homogeneous medium of constant permeability and fixed width. And then you can, even though it's three-dimensional, you can model it as essentially two-dimensional because the fluid is so pushed together. And this, so this induces a free boundary problem, which is the Healy-Shaw problem. And another example that's very similar to the Healy-Shaw problem is the Muscat problem. And here you have two incompressible and immiscible fluids, which means they don't mix. And so one fluid is gray and the other fluid is blue in this first picture. And the gray fluid is denoted by the domain D1, and the blue fluid is denoted by the domain D2. And here we set the viscosities to be different or possibly different. So the viscosity mu1 and mu2 are different in each domain, and the density is given by this sharp front type density, where rho1 and rho2 are thought of as constants. And if you take these initial data if you take these initially, then they stay that way. So the sharp front initial data for the porous medium equation remains a sharp front over time. And then the question becomes to study the evolution of the boundary of this problem. And there are two cases. One is the circle case, where the boundary of D is a closed curve or a surface. And another case is the flat case here, which is very similar, except you think of you're in the whole, the curve extends through the whole of R2, and the boundary is a curve that vanishes. It goes to a constant at infinity. And this gives you the Muscat problem, which I've studied quite a bit so far. And now I'll give you some pictures again. So Muscat himself, who the Muscat problem was named after, was actually an oil, he was a petroleum engineer, and he was thinking about the problem of pumping oil out of oil sands. And so that's where this problem comes from. And then again, this is the Hilly-Shaw cell, or some figures that you could see in the Hilly-Shaw cell, and you often see viscous fingering as a type of phenomenon that's studied using these free boundary problems. So those are the pictures. And now we got up to the Peskin problem, which is the Stokes immersed boundary problem. And we have the red blood cells that we're trying to study. So when I gave this talk the last time, at the end of the talk, I got a question about whether anyone studies this equation in like material science or engineering community. So after that, I was motivated to add this slide. Not that it proves anything, but it shows this Stokes immersed boundary problem, which we're now calling the Peskin problem, was sort of initiated by Charles Peskin, and this is his PhD thesis from 1972. This started with a PhD thesis, and then this is a paper published in 1972, Flow Patterns around heart valves and numerical method. And then this is a paper in 1977, numerical analysis of blood flow in the heart. And then this is sort of a summary paper, the immersed boundary method from Active Numerica in 2002. And this is another reference from MathSciNet, the last one for the immersed boundary method paper. So I wanted to answer the question, or at least try to give you a brief answer to the question of whether or not this equation is studied a lot by the outside of analysis PD. And so my answer to that question is, well, these are all different papers, and look at how many citations each of these individual papers has. And so the answer is yes, it's incredibly extensively studied. And also this is MathSciNet. So these are the citations for this paper. MathSciNet is just 951, which is high. And these are the citations for this paper in Google Scholar. So you can see that there's a lot of study of this approach outside of MathSciNet, so outside of normal math citations. So in many other areas of science and in medicine. Okay, so that's my justification, and now I'll explain to you a little bit about the problem. So this is the Stokes immersed boundary problem, and it has a velocity field U, and you have an immersed boundary. So you have Stokes flow in a 2D open domain that's denoted by D on the outside and D complement on the inside, where D complement is R2, not D using the boundary. And you have a one-dimensional elastic string, gamma, which is the boundary that's parameterized by theta. And the position on gamma is x, which is a two-dimensional vector, is x of t and theta. And the force is f of theta. And so here's the position x on the boundary, the boundary is sort of traced out like that here. And the problem that we want to find the answer to is find the velocity u and the elastic string position x. And so that's we want to solve this. And of course, there's a PDE. So here is the sort of first formulation of the PDE. So you have a Stokes fluid with viscosity mu that's satisfied on D union D complement, and it's mu Laplacian of u minus the gradient of P equals 0, and u is incompressible. So u dot, the gradient dot u is equal to 0. And then you have these jump conditions across the interface. So sigma is this stress tensor, and it's given by this quantity here, mu times the gradient of u plus the gradient of u transpose minus p times I, where I is the identity matrix. And then this bracket notation denotes the jump across the interface. And so the jump across the interface of the stress tensor in the uninormal direction is equal to a force law that we call FEL times the length of the derivative of x. And the jump across the interface of u is equal to 0. So u is continuous across the interface. Those are our conditions. And so these jump conditions represent the no-slip boundary condition and the force balance boundary conditions on the interface gamma equals the boundary of omega. And then there are a couple situations that you consider. One of the results I want to talk about today is for the general tension force law. So the force, in that case, for T, an arbitrary nonlinear function, the force law is the derivative with respect to theta of T of the modulus of x times the derivative of x over the modulus of the derivative of x. And the simple tension force law is that F is a constant times the second derivative of x. And this arises from the general tension force law if this tension T is linear. Okay, so this is one formulation of the Peskin problem. And now I'll give you a second formulation. And this is the immersed boundary formulation. And this is the formulation that sort of made this equation so famous in the numerical and applied math community. And so I have the same picture here. And the idea is that you can sort of look at weak solutions to the Stokes problem that I showed you on the previous slide. And you can write this as one equation. Then you can plug in the boundary condition, and now you have the incompressibility condition plus this formulation. So here the force balance condition at gamma on the boundary is treated as an external singular force field supported on gamma of T which is equal to the points x of theta. And so you're integrating over theta, and you have this delta function of x minus some capital X of theta. And on this side, you're evaluating u and p at lowercase x and t. So this is u is u of x, lowercase x. So this is this x. And then you have this, the general force law is plugged right in here. So this was a really nice way to simulate this problem in a computer, because you can solve the Stokes equations and you can simulate this in one step. And so this, without saying too much about it, this formulation has proved to be very useful computationally. And it was this expression was sort of the foundation of the immersed boundary method. And there's a third formulation that is very useful for doing analysis, but has also been used computationally. And this is the contour dynamic formulation. So another property of the fluid that is well understood is that the string moves with the flow. And so that in that sense, the time derivative of x can be expressed as u evaluated at capital X of theta and t. And that, but here u and x are both unknowns, but you can invert the Stokes operator in the whole space, and then you obtain this expression for the contour dynamic formulation of the Peskin problem, and it's that x is equal to this non-local integral operator of this function g times the force law, and you integrate over t over all d alpha. So here the kernel g of x is called the Stokes slip, and it can be written exactly as this. So g is equal to minus log of x times the identity matrix in R2 times x tensor x divided by x squared. And this is the contour dynamics formulation of the problem. And this has been very useful for doing sort of analysis on the Peskin problem. And let me give you one more sort of explanation of this problem. So numerically, here's some numerical simulations that were performed by my colleague Yoshiro Mori a long time ago, and I took these pictures from him. But this first numerical simulation is kind of where you start, and then you are looking for convergence here in the second picture, and I'll explain that in a moment. So an issue with the immersed boundary problem or method is that it experiences low order numerical convergence. And this was studied in particular by Mori in his 2008 paper. And so what you're seeing here is in green is a very, very rapid exponential or spectral convergence away from the interface. And then this very slow, jaggy convergence close to as you approach the interface. And so low order numerical convergence in particular means that existence and uniqueness results with low regularity can be very useful for both theoretical justifications and also perhaps for motivations to develop new numerical schemes. So in particular, if you try to prove existence and uniqueness in some Sobolev space and you don't care about how much regularity you're using, you just want to prove the first result or the best result or something like that, then it may not say a lot about the immersed boundary method from the numerical point of view because there's a connection between the order of convergence of your scheme and the regularity. So it's important not just from a sort of I want to prove the lowest regularity possible and flex my muscles point of view, but it's also important from a physical point of view of the convergence rate of this problem to study low regularity solutions and low regularity existence and uniqueness results. And so I wanted to mention that sort of applied mathematicians, including Yoshiro Mori at the University of Pennsylvania and Johnny Guzman at Brown, have expressed importance of future analytical work in this direction and enthusiasm about that. So in this case, sort of the applied community is interested in seeing analytical work. Okay, so I want to tell you about critical local well-posedness for the fully nonlinear Peskin problem and some analytical work that I've done. But first, I want to mention some related works for the Muscat problem at critical regularity. So there's this old paper, this 2013 paper by Constantine Cordova-Gancedo, me, on global existence for the 2D Muscat problem, and then this was generalized to the 3D Muscat problem in 2016. We also added Rodriguez Piazza as a collaborator. And then recently, there's been a lot of attention, welcome and attention to be brought to the Muscat problem with critical or slightly subcritical regularity. And this is just a few of the papers, but there's this paper by Wynn and Benoit Passador that a paradifferential approach for well-posedness to the Muscat problem that was published in 2020. And they prove in a very general framework local well-posedness for slightly subcritical initial data. And then Wynn wrote a couple more papers on well-posedness for the Muscat problem with surface tension, also in 2020, and global solutions for the Muscat problem in the scaling invariant Besov space, B dot infinity 1, 1. And so this is for small data, global solutions. And this is critical initial data. And this is slightly subcritical initial data. And then these three papers are about critical local well-posedness and global well-posedness for large data and global well-posedness for small data for the Muscat problem. These are papers are by Alizard and Kwok Hung Win. So there's two different people here, Kwok Hung Win and Hui Win. And these three papers came out recently, and they prove in different spaces for critical initial data, local well-posedness, and global well-posedness. Okay, so that's what I want to say about Muscat, and that sort of motivates some work for Peskin. And here are some results. This is, as far as I know, other than the work I'm going to talk about that I did with collaborators, this is all of the analytical PDE work for the Peskin problem, these 5 papers. So the first paper is Mori, Rodenberg, and Spern proved well-posedness and global behavior of the Peskin problem of an immersed elastic filament that was published in 2019. They prove local well-posedness in Holder spaces that are sort of slightly subcritical. And at the same time, Fangwell Lin and Tong proved a similar result in Sobolev spaces. So I think this paper works in H5 halves, which is not slightly subcritical, but it's subcritical. And this paper works in C1 gamma, which is slightly subcritical. And this paper also proves the smoothing effects. I should also say all of these works study the simple tension law case that I told you about, where the T is linear. And then Tong himself generalized the work of Lin and Tong and studied the singular limit and error estimates. So he proved error estimates for the approximation to the problem in Sobolev spaces in H5 halves. And okay, so this team of Gancedo, Bernero, Belson, and Scribonia studied global existence for a related but not for a model problem that they call the N-Peskin problem. And they proved global existence for small data in a critical space for this model problem. And then Chen Chen and Kwok-Hung Win. So Chen is Win's PhD student for the simple tension case. Recently proved local existence for large data and global existence in this very, very large Besov space, B.1 infinity infinity. This is a critical Besov space. And this is kind of is kind of like the analog of the kinds of results that you have seen for Navier-Stokes in the last 10 years in very, very large Besov spaces. But it's a very nice paper. But that and I know Win, and he's a very nice guy. So this is what's known, or what has been known. And so let me tell you a little bit about the boundary integral formulation of the Peskin problem. So all of the previous results were for this case where T is linear. So T, all of the previous results study the case when T is a linear function. And we want to look at the case, which is the simple tension case down here. We want to look at the case when T is fully nonlinear. And so the boundary interval formulation for the general force law is this equation that I'm writing here. And now I'm writing x prime as the theta derivative of x to simplify the notation. And I'm writing delta alpha of x theta is x theta plus alpha minus x theta. So the standard partial difference. And then you can write the equation like this. And here for z and R2, g of z is this Stokelet, which I'll write again like this as g is g1 plus g2. Excuse me, an average drink of water. And g1 is 1 over 4 pi minus log z times the identity matrix, and g2 of z is z times z over z squared times 1 over 4 pi. And then in the simple tension case, TR is K0 times R, and the equation above takes the form dtx is K0 times g of delta alpha x times the second derivative of x theta plus alpha d alpha. And so this equation looks very bad to study at critical regularity due to the second derivative appearing on the right-hand side. And so that makes things look horrible if you want to understand the equation at critical regularity. And so one of the observations that we made, now this is the joint work with Cameron. With Stephen Cameron. One of the observations that we made is that there's a cancellation. So we propose to write the equation in an equivalent formulation that will cancel out the terms featuring the second derivative. And when we realized this could be done, we were very enthusiastic. So if you integrate by parts against the g1 function and leave the g2 function alone, then you get this expression. So you take one derivative off of x and move it over here, or sorry, you actually take two derivatives off of x and move one of them here and the other one here, and that's how it ends up as. And then you leave this term alone. Then after doing some calculation, you get this equation at the bottom, and this equation has a delta alpha of x here. It has this tension term here, and then it has a kernel here, which is a bit complicated, but it only involves x or derivatives, or one derivative of x. It doesn't, there's no second derivative appearing anywhere in the equation. And this sort of observation that we made was sort of fundamental to everything that we did afterwards. And so this is a very nice way to write the equation for us, because now it looks like a diffusion operator, a non-local diffusion operator with a kernel that depends on your unknown. That can also change sign, but that's okay. And okay, so it gets more complicated, but actually better at the same time. So then this, one of the things we figured out also is that this property of cancellation of the highest order derivatives is also satisfied by the equation for the derivative. So you can take the derivative of the equation and derive that it satisfies this vector equation. So the time derivative of the spatial derivative is the integral d alpha over alpha squared of k, this kernel k of x times delta alpha of t of x prime. So this, where t is this thing that we're calling the tension map. It's the calligraphic t of the modulus of z times the unit vector z. And the kernel down here is this complicated vector kernel. So k is a matrix and it's operating on a vector, and you get a matrix coming out of this. So this is and this is what it looks like. I won't sort of read it to you or anything, but so it's this is the kernel, and it's and these are the operators that come out from it, and this d alpha thing is different, so it's sort of like a derivative, but it's not. It's only taking a derivative when alpha goes to 0. So this the thing to notice here is that this is a super complicated expression, but it only involves derivatives of x, or things that are of the order of the derivative of x, like d alpha x. And so it's super nice in that way, even though it's a complicated vector expression. Okay, so a model to understand this equation would be the vector valued fractional porous medium equation in the following sense. So for small alpha, the integrand of the dt x prime equation is approximately given by delta alpha of t of x prime over 4 pi alpha squared. And so the equation on the previous slide is a basic model problem for it would be this fractional porous medium equation, this vector value fractional porous medium equation that I'm circling here for T, the tension map that I showed you here. So to the best of our knowledge, this equation has not been studied before at all, but some things have been studied in this direction, and the positivity and monotonicity assumptions that we'll make on the tension are both physically motivated, as well as the same assumptions that typically appear in the porous medium equation in order to ensure the ellipticity of the problem. Okay, so I'm not going to read this slide to you, but I'm just going to say that the porous medium equation, the scalar porous medium, the scalar fractional porous medium equation has been studied, and here are some papers about that. And the local vector valued porous medium equation has also been studied. So this is, you replace lambda or the square root of the Laplacian with the Laplacian itself, and then the local vector valued porous medium equation has been studied, but the fractional vector value porous medium equation, we're not aware of studies of it. Okay, so now I want to tell you some scaling critical spaces. So the scaling for the Peskin problem, or one of the scalings for the Peskin problem, is this one. So x lambda is lambda to the -1 times x lambda t lambda theta. And so if you have a solution x to the Peskin problem and you plug in this rescaling, you get another solution to the Peskin problem. It so happens that this rescaling is the same as the rescaling for the Muscat problem. Here are some scaling critical spaces for the Peskin problem. One is what we call the chord arc number. It's the infimum over theta and alpha, where alpha is not equal to 0, the difference of x theta plus alpha minus x theta over alpha. This is a quantity that is essential to these types of problems, and you need this to remain positive in order to make sense of the equation. If the curve takes on the same value at 2 points, then this will be 0, and then the right-hand side of the equation is no longer well-defined. So another scaling critical space is the Lipschitz space W.1 infinity, and another scaling critical space is the Wiener algebra. Other scaling critical spaces are BMO1 and VMO1. If you know what those are, I won't discuss them anymore. And another scaling critical space are the homogeneous Besov spaces, B.1, 1 over P, PR for any P and R in 1 infinity. And so we will emphasize this space as B dot 3/2 2R for R between 1 and infinity, and H dot 3/2 T, because those are L2 based spaces. Okay, so these are scaling critical spaces, and here are some solution spaces. So we use the LQ mix norms, where you first integrate in theta and the p variable, and second integrate in the t variable on the outside for p q between 1 and infinity. And I'm going to use these Besov spaces, b dot s p r for s between 0 and 1, and p q and r between 1 and infinity, which are, so you take LP of the delta of f, and then you integrate over d beta divided by the modulus of beta times beta to the power s. And this is taking s orders of derivative, and you sort of separate out the integrability that you use for the function f and the integrability you use for the derivative in terms of p and r. And these are a generalization of Sobolev spaces that can be useful. And then we'll also use these so-called Chemin-Lerner mixed regularity spaces, where you have LQ tilde and B dot SPR. And the point of these spaces is that the time integral is inside of the regularity integral, but outside of the theta integral. And the point observed in this paper by Chemin and Lerner is that you sort of can do this when you're studying fluid problems. And this space is a little bit stronger than if you were to normally put the LQT norm on the outside. So we're going to use all these spaces. And so we're also going to use this logarithmic regularity trick. So you have Besov spaces with regularity on the logarithmic scale. And so you introduce this mu function. And then you add like a logarithm of additional regularity over a normal Besov space. And this mu is a function that satisfies that it's increasing, and this limit goes to infinity. It satisfies the doubling property, and the function mu over log of 4 plus r is decreasing, strictly speaking, on 0 infinity. So this function does not grow any more than a log. And then this adds a sort of logarithm of regularity. This kind of log regularity was spaces were motivated by the Alazard and Wynn papers that I mentioned to you earlier from Scott. They did this and they can basically prove critical local well-posedness by proving logarithmically subcritical local well-posedness and using a well-known theorem that says that any integrable function is weighted integrable also if you're willing to add a small logarithmic weight that depends on the function itself. And we are sort of doing the same thing. And we're doing it in this scaling critical Besov space. So this is our space. It's V2, 1, 1/2, and it's the space of the derivative of x prime, and it's d beta over beta to the 3/2 times the difference of x prime in L2. And then, okay, so this is a weak solution. So we take an initial data in the space, which satisfies the chord arc condition, and we call it a weak solution of the Peskin problem with fully nonlinear tension T and initial data x if T of x is in this space, and the chord arc condition is satisfied over time, and there exists a function y such that the equation is satisfied in the weak sense. Okay, and then we say that x is a strong solution if x is a C2 and solves the equation pointwise with the chord arc condition satisfied and the limit of the solution converging to the initial data in L infinity going to 0. So it's a strong solution. And okay, so here's our first theorem. This is a critical local existence. So we'll let x be an initial data mapping T into R2 with x prime initially being in the space V dot 1/2, 2, 1, and the chord arc condition being satisfied. And then let the fully nonlinear Taylor scalar tension satisfy that it's C1, 1 loc with T prime greater than 0 for all R greater than 0. This is needed to have a well-defined, well-posed problem, sort of. Then there exists a time T such that there exists a unique weak solution x to the Peskin problem, which is also a strong solution. And furthermore, for any beta between 0 and 1, x is in C2 beta loc in all variables. And additionally, if t is in ck gamma loc for k greater than 2 and gamma between 0 and 1, then x is in ck plus 1 gamma loc. And so then due to the structure of the equation, x in ck plus 1 gamma is optimal regularity for t in ck gamma. We prove this theorem by proving a quantitative version under more restrictive assumptions on the tension. And so I can tell you a bit about that. So this is a sort of quantitative, logarithmically subcritical type theorem. And so consider initial data x, x0. It satisfies that in this Besov space, it's bounded by a constant that could be large, but with a mu, and let the tension map satisfy the tensions in W1 infinity. It satisfies the ellipticity condition. And then there exists a time depending on all the parameters and the W1 infinity norm, such that there exists a strong solution to the Peskin problem with tension T and initial data x, and the solution satisfies for universal constant C this energy type inequality that you see here when it shows up with the ellipticity condition. Okay, so we also have quantitative smoothing. So this is a quantitative smoothing theorem. So for any small time greater than 0, the solution is in C2 beta for any beta. And if T is in ck gamma, or T is now the tension map for some k greater than 0, and gamma between 0 and 1, then x is in C, k plus 1 gamma. So you get the optimal smoothing effects. And so we have sort of two uniqueness theorems. The first one is uniqueness in a slightly less regular space. And so for any logarithmically less regular space, so if you're unique. So if you have existence in some, if you have quantitative existence in some b1/2 mu2/1 space, then for any smaller mu in the sense of this theorem, of the conditions of this theorem, then you're unique in a slightly smaller space. And this is a short proof. And we also have a sort of long proof, strong continuity estimate in the at the same level of regularity for the initial data, but requiring an additional derivative bound on the tension. And so you have a strong continuity estimate for solutions at the same level of regularity as the initial data. In this way, if your tension is a little bit more regular. Okay, so let me say, let me say something. Okay, so I want to mention kinetic theory. So I wanted to say that, so for me, studying this equation at critical regularity, it was important to use these Besov spaces there so the critical regularity was motivated by the science and by the applied math and by the low order convergence of the immersed boundary problem, and then using critical regularity sort of for us, it was most useful to work in Besov spaces. They were more sort of the problem was more solvable in these spaces. It wasn't just for the purpose of getting the lowest regularity possible. And so some motivation from kinetic theory are these papers working in Besov spaces for the Boltzmann equation, and this paper that I worked on with Duan and Liu and Sakamoto in the critical Wiener algebra, which is related to Besov spaces in ways that I won't explain. Okay, so yeah, and the higher regularity proofs are based on proofs of higher regularity for the scalar fractional porous medium equation. In particular, there's this paper by Vasquez de Pablo, Quiros, and Rodriguez studying the nonlinear fractional diffusion type equations like the fractional porous medium equation. And it turns out that their proof helped us to prove the regularization for the vector valued equation that we're studying, even though this is for a scalar valued equation. Okay, so lastly, I want to tell you about I want to just tell you that we have a result for small data globally in time with the other team in the viscosity contrast case. So this is the, now we use the linear tension law, and we have two different viscosities. And then we have a global existence theorem for small data close to equilibrium in these critical regularity spaces. That is right there. And in this case, as I like to do, we estimated the size of the initial data precisely, and it's and it's not like super big, but it's not like super small either. Well, with our method, which is not really optimized for the size of data, we got like the size of the initial data is on the order of 10 to the third, and there's a reason why this tails off to 0 in both directions as this parameter mu goes to 0, and that's because the problem is sort of not good in each of these cases. It's not so it's only important. It's only reasonable to study the problems are here. So that's why that happens. Okay, so maybe I can stop. So thank you very much.
Thank you very much for this very interesting talk. So are there any questions or remarks? So if this is the case, please unmute and turn on the camera.
Hi, Bob. Thanks for the great talk. I have one question. So are there other steady states beyond this flat case, whether or not the circuit type of
that's a very good question. So as you know, the question of steady states for these problems really depends on the regularity class you're working in, and so if I go back to so for the Muscat problem, it's supposed either on the sphere or in the whole space type situation, a closed curve or not, or a flat curve. For the Peskin problem, is really a closed curve, because I mean you can pose the equation on with a non-closed curve, and this equation that I wrote down and that we derived, say like here, this equation can be extended to the whole space easily, and it's the same equation just integrated over the whole space. But if you want to talk about red blood cells and the applications, then it's really just a closed curve. And okay, so in that case, Mori, Spirn, and Rodenberg, part of this is 80-something page paper that has a lot of things in it, and one of the things in it is a proof that at least in C1 gamma, the only steady states are circles. So, but like for example, for the Muscat problem, it's known that, and for the Healy-Shaw problem, so if you're at like critical regularity, in the circle case, the only steady states are circles. But if you go to very low regularity situations, there are other crazy steady states so there are a collection of other steady states.
Very interesting. Okay, I see. But do we know, for instance, for this Peskin problem, the circles are stable? Do we know that? I mean,
yes. So that's the proof. These so where should I go? Here. So this paper proved the circles are stable.
Okay.
This paper proved the circles are stable in their regularity class, and this result that I didn't talk about too much. Also, in a critical, the important point here is that this is a critical regularity. This paper also proves exponential convergence.
I see. Great. Okay. Thank you. Thank you.
You're welcome.
Yeah.
Okay. Thank you very much. Are there any more questions?
Bob?
Yes.
Please go ahead.
Can I ask a question?
Yes.
So it's just to make sure I understand. If I understand your motivation for it, or is there a higher dimensional version of it that would
Yes.
look at the evolution of a surface?
Okay, so that's something that we are studying. But I mean the answer is yes. So here, and I'll show it to you, or I can tell you sort of. I mean, so pose this problem in 3 dimensions or n dimensions, and there's your higher dimensional version of the problem. But so there's in terms of research, there's if you want to look at numerical, and I'm not an expert on the numerics at all, or in particular the numerics of this problem, but if you want to do numerical analysis in 3D, it's very laborious and takes a long time on the computer. And so the problems that if they study a 3D problem, they do it in a very special situation where they reduce a lot of things to make it easier to solve. There's you can write a 3D version of this problem, and I'm actually studying that with Eduardo Garcia Juarez and Mori and Pochan Kuo, who's a graduate student at Penn. And it's a lot more complicated, but there are no analytical results in 3D as of now. But we think we can do similar results in 3D.
Okay, great. Thanks.
Okay, are there any other questions or remarks? I have a quick question. Maybe I missed it. You mentioned that also your formulation is used for numerical methods. So, I mean, are the results that you prove, are they going to help with, for example, the numerical analysis or convergence of numerical methods? Because you said they observed these instabilities there, so I assume, and they were
we
interested.
hope so.
So
I mean, the primary numerical formulation is this immersed boundary formulation here.
Okay.
And I mean, we sort of hope that, I mean, and Mori, who is my collaborator, is a applied mathematician, and he is very interested in numerical work, and he's also very interested in analytical work, and he wants to do analytical work because he thinks that it gives, first of all, it gives theoretical justification for the system. So if you have existence at low regularity and you have smoothing effects, then you can argue that all of these 3 formulations of the problem are equivalent.
But you only have the smoothing effects, sorry, if the tension is sufficiently nice, isn't it? So that's...
Okay, no, well, I stated the first, so no, I mean, okay, so there's yes. So for linear tension, you have smoothing effects. In that case, the tension is as nice as you want. And for nonlinear tension, there's a trick. So it's in the paper, but I didn't have time to mention it in the talk, but there's a trick to get the same results for much more general tensions than in the quantitative version of the theorem. So the qualitative version of the theorem, let me see if I can find it, assumes the tension is C11 loop. And this is all you need. So you have the smoothing effects, and if you're C11 loop.
And you said then all the formulations are equivalent.
But you have the smoothing effects up to here, and then if you're here, then you can argue that all the 3 formulations are equivalent because you're sufficiently regular.
Okay. Thank you. Just curious. Any more questions or remarks? If not, I would like to thank Robert again and all the speakers of this afternoon session. I'm not aware of any other announcements. If there are, Clément?
Not that I know about. We'll start tomorrow at 9 with the talk of Laurent Desvillettes. And that's it, I guess. I've put on